Okay, welcome back, guys. We are now on to 5.2. I'm just gonna write general double integrals. And the idea is just that we don't need to restrict ourselves to rectangular domains. I'll try to make this clear. Why a rectangular domain? Well, it's very easy to grid out a rectangular domain. And in particular, if we get these lower bounds and upper bounds, A and B for X, and then maybe a C and D for Y, the integral has this nice a form where we have these constant bounds, some function f of x, y. And whatever the function is, it exists over this nice rectangular domain. Now, let's imagine you had instead maybe like a circle, and you wanted to somehow come up with a way of integrating functions over just this circle. So let's say this is the function over your circle here. Well, you can still interpret the integral as the volume over the domain that lies under the graph of your function, right? That's still a clear geometric meaning. And so the only question is, how can we set up some mathematical expressions to evaluate that? So as a first step, you can imagine that the function equals 0 outside of your circle. And that you therefore can think of it as existing over an entire range, A, B, C, D. So let's say the red function is G, and we make a new function F where they're equal. I'm just going to say in the circle. And I'm just going to extend F by saying F is 0 everywhere else. Right? So it's piecewise defined. Well, then if the disk, we'll call the disk D, and the rectangular region R, then we should have the integral over the disk of G is the same thing as the integral over the rectangle of the function f. Right? We're just saying extend G to an entire rectangular domain. Now we can actually talk about things like the integral over that rectangular domain. And we've made it to 0, in everywhere that doesn't really matter. So that shouldn't affect the integral, right? Those are rectangular prisms of height 0 there. So that's exactly what the integral of G should be. And now something's going to happen. I'm going to try to make it as clear as I can. If you did this this way, you would say this integral, let's put y on the outside. So the last lesson, I really tried to hit this home that you can think of integration as occurring first in one direction and then in the other direction. There's only two directions right now. I want to try to go a little bit more in detail into what that looks like here. So let's go over here. Y goes from C to D, right? Y goes from C to D. So Y starts off down at C over here. And we integrate in X, this function that I'm drawing right now, which is zero. It's zero everywhere. And maybe we go up a little bit to a new value in Y. And we integrate in X, right, from A to B. So here, this first line, we're integrating from A to B. It's just a function zero. This one here as well, we're just integrating from A to B. It's just a function zero. But then let's go up to maybe like right here. And I'm going to call that point, I'll just call it Y initial. You're integrating zero, and then boom, you hit the region that really matters, and you see some non-zero values. So if you think about that, you're really going to find this area here, the area of that sliver there. And then you keep going and you get zero. So along that line, you integrated from A to B. F of X comma, I'm going to run out of space here, but Y initial dx, right? You fixed Y initial and you just have a function of X. Now, here we go. This is going to be the hard part. There's a different way you can find that same integral. Let's try to use a different color now. You can say, well, what is this starting value here? And what is this value here? For the moment, I'll just give them names like maybe X1 and X2. And you could integrate just from X1 to X2, right? Because who cares? The other part's zero anyways. And now we can just write G. And we get this. Look, we get an integral here. It's the same integral. Who cares? We're integrating the function G now. But we haven't gone all the way from A to B. A bunch of that was wasted. Sure, question. Are these bounds good everywhere? What if I change my Y value? Let's definitely gonna run out of colors in a second, but now let's go to a new Y value. Let's call this guy Y1. Now you really want to integrate from this starting point to this endpoint. Whoops. You have different bounds in X. These guys don't work anymore. So here's the leap. There's a function right here. It's a function of y. We can call that function x1 of y, or you can call it h1 of y. Let's go h because people are going to confuse the x's. Let's call it h1 of y. And there's another function right here, and that one we'll call h2 of y. And instead of integrating, ready for this, from a, well, there was one smaller zero. Let's go, let's put instead let's just put C there and D there. And let's say this is A and this is B. Instead of integrating from C to D and integrating from A to B, right? Because there's all of this zero space, all of this part is zero here. We don't care about it. And this part's also zero. We can instead say, look, take all the y values between C and D, but x only needs to go as low as h1 of y and as high as h2 of y. And in this region, we can write g because g actually exists everywhere in there. This is the same thing. I'm going to say note, it's kind of obvious, but the bounds depend on y. We have a function here and a function here. Because if you change to a different y value, you may have a different bound, different lower bound, and a different upper bound. Okay, so here's the deal. A region is called type 1 if, so first I'll draw a picture. It looks like the area between two functions of x. So that region there, look, here's like an H1 or notation that the book uses. They use G. I'm gonna put G here. G1 of x, and this appears G2 of x. Right? The region that I've drawn here is the space between these two graphs. So if it can be written, so there's a few different ways of writing this. All points x, y such that g1 of x is less than or equal to y is less than or equal to g2 of x. Right, so if you take a point like right here, that's a point x comma y, and the y value is between g1 of x and g2 of x. Or you can just say if it is, we can just say this in mathematics, is the region between two vertical lines, so these two, the left and right edges, two vertical lines, and the graphs of two continuous functions, two continuous functions, G1 and G2. And of course, uh, I'll just say this, we need that G1 is less than G2, right? And then we'll just get the other one out of the way. Type 2. If, same idea, but now it's between two functions of y. So there's some function of y, some other function of y. And then the book, I just want to make sure that I stick with their notation. Here they use h, yeah. So this is h1 of y. This is h2 of y. I'm going to just put dot, 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 same. It's the same as everything over here, except now it's that the x, except that we have h1 of y is less than or equal to x is less than or equal to h2 of y. So now it's all the points between these two graphs and two horizontal lines, right? And if this is, if you have these two, then we have furthermore, um, if this region here is R, then the double integral of a function f over R can be written this way. So I need a lower bound, let's say A, and an upper bound B. X goes from A to B. Y goes from G1 of X to G2 of X. And then over here, what we would say, if now that region is R, then the double integral over R of a function f dA can now be written instead. We'll take, so one more thing, obviously. We'll have y starting at C and ending at D. Y goes from C to D, and X goes from H1 of X, Y, blah, blah, blah. H2 of Y. I'm going to do some examples in a second that hopefully make this clear. This is dx, this is dy. And be very, very clear, spell something out here. Note the inner bounds. So in H1, H2 of Y, G1, G2 of X depend only on the outer variable. It's crucial that you understand this. If the outer variable is x, dx, the inner bounds can depend on x. If the outer variable is y, the inner bounds can depend on y. No other dependencies are okay. You can't have extra y's in here or extra x's in here. Okay, let's just immediately try to get some examples out because this is a lot of abstraction. This is just for describing a region, so we're not setting up an integral yet. Let's say that this is x and this is y, and here's one line, and here's another line. And let's go between the two of them. Let me just ask you, does it look like this is a type 1 region or a type 2 region? Trick question, it can be both. Let's call this line y equals x cubed. And this one, it's got to be the cube root, right? No, they use the square root. Okay, cool. Y equals root x. Is this region type 1? Well, there is a lower bound, 0. And then these guys are equal at 1. X cubed and root x are equal when x equals 1. So there is a lower bound in x and an upper bound in x. My dx on the outside. And then within that interval, the region is absolutely the region between the graphs of two functions. So we can take y going from the lower one, which is x cubed, to the higher one, which is root x. We don't have a function to put here, but that's what we would put dy. So we can write this instead, if you want, as r equals, I like to write these things out. You don't have to if you don't want to. All the points such that we'll do both. X is between 0 and 1, and y is between x cubed and root x. And I'm going to move this dx closer. It's too far away. You don't need to write it that second way. I think this way is better. It just really hits the point home. But now here's the next thing. Is it also type 2? It sure is. This line right here can also be written as x equals y squared, right? If you square both sides. And down here, this line can also be written as x equals the cube root of y. And so I can take y from 0 to 1, dy. And now the inner bounds can depend on y. And I would use the lower bound is y squared. The upper bound is the cube root of y. This is all dx. And then I could put some function in there, but, we don't have a function to integrate. Or if you want, you can re-express the region R as all points x, y, such that y is between 0 and 1, and x is between y squared and the cube root of y. These ones are not as important because we're not really doing set notation. We're interested in doing double integrals. So the integral versions are much better. Okay, so if you're asked to express an integral over this region as though it's type 1, here it is right here. Down here, as though it's type 2, it's right here. And then let me just say that theorem we saw yesterday, Fubini's theorem, applies here as well. These guys are equal by Fubini's theorem. No matter which order of integration you do, you will always get the same final volume, same final number. At least when the functions are well behaved enough, if they're continuous, for instance. Okay, let's try to do an example that actually involves doing integrals. So, boom, example. Let's see what we got. Yeah, let's try this one out here. Hold on. One thing they say. No, 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 no. Yeah, okay, I'll do this example. So 3x squared plus y squared, with respect to the area, over the region D, where here they give D this way, x, y, such that uh, -2 is less than or equal to y is less than or equal to 3. And then y cubed minus 3 and y, oh no, y squared. Y squared minus 3 less than or equal to x less than or equal to y plus 3. Okay, what have they given us? They've given us a region that we want to integrate over, a function to integrate over it. And the region is not a rectangle. So the stuff from yesterday doesn't apply. It's immediate from the way they wrote it that it is a type 2, right? Because they've got x expressed as being between two functions of y. So let's just set this integral up with y on the outside, and we'll use those bounds that they gave us for x, no, y squared, excuse me. And then we have to integrate the function they gave us, 3x squared plus y squared, dx dy. Okay, we got it set up. Just freeze there. This is really what you're learning, how to set it up. From here, it's going to be super easy to evaluate. We're just going to do a bunch of basic calculus. We'll start with the inner integral. I'm integrating with respect to x. Ah, do they? Okay. I'm really surprised at some of the problems that this book gives in terms of difficulty. Yeah, whatever. So right, x is the only variable. 3x squared integrates to x cubed. Here, y squared is a constant. If you integrate a constant, you just append a new factor of x. So this is the right integral here in x. Got to plug these bounds in. Okay, first you plug in, whoops, y plus 3 for x. And then you have to subtract off what happens when you plug in y squared minus 3 for x. dy. Right, so first you plug in the upper bound everywhere for x, and then a minus sign, and then the lower bound everywhere for x. Okay, this is just a bunch of ridiculous expansions, but actually some of this we don't have to expand. So I'm going to integrate some of it. Y plus 3 cubed, you can integrate that. That comes out to be y, whoops, y plus 3 to the 4th over 4. Uh, plus y cubed is y to the 4th over 4 plus 3y squared is y cubed. I'm going to keep going with this stuff here. I get y to the fourth. That integrates to y to the fifth over 5. Minus 3y squared. That integrates to minus y cubed. All of that needs to be evaluated between -2 and 3. And then the only thing that I actually need to do any work on to integrate is the y squared. So I'll put a minus on it. I screwed up a little bit, didn't I? That should be minus. That should be minus y to the, this minus sign has to get distributed. And then that's a plus y squared minus, because minus 3y cubed, but that, I mean, excuse me, minus y cubed, but the extra negative sign there. Okay, so everything other than this here, you can integrate directly. So I've done all that on the side here. This all needs to be evaluated. Y squared minus 3 cubed, you can't integrate that without doing a little bit more math. So I'm very frustrated at them for putting these kinds of complicated things in. Okay, let's go for it. This does not look worth doing. Let's the easiest way to do this. Well, we can just do it. 3 plus 3 is 6 to the 4, 36, 216. This is no. I think it's not worth doing out. 1 second, I'm just gonna use a calculator. All right, this is 324 plus 3, 9, 27, 81 over 4 plus 27 minus 243 over 5 plus 27 minus -2 plus 3 is 1. This is just 1/4. 2, 4, 8, 16 divided by 4 is 4. -8. 2, 4, 8, 16, 32 plus 32 over 5. I'm gonna actually stop right here. Minus so plus 8. Okay, this all is that there. I'm gonna let you guys just work that out because it's not really worth lesson time. And let's just be clear here. This guy, you've got to expand this. So y to the fourth minus 6y squared plus 9 times y squared minus 3 dy. And then just one more step. Minus -2 to the 3. And then you've got y to the 6 minus 6 y to the fourth plus 9y squared minus 3y to the fourth minus 18y squared minus 27 dy. And then you can integrate all of that. I think by now you guys can see that when I give you problems on quizzes and exams, I don't expect you to carry out this much arithmetic. It's kind of a ridiculous waste of time. But from here, you can see y to the 7th over 7, y to the 5th over 5, y cubed over 3, y to the 5th over 5, etc. You can integrate all of this. I'm going to leave the rest for you guys to work out. Let's do another problem. Let me just make sure I didn't skip anything. Okay, from the top, you are given a function you want to integrate. The way this region was expressed, you can see immediately that it's type 2. You set the integral up correctly. That's what we're learning today. And then you've got to muscle through the calculations. Hopefully, they're not as bad as this problem. Let's try another one. Yeah, this is a good one. Okay, here's a drawing. The region looks like this. Is this type 1 or type 2? They give us a few things. This is 0, comma 4 right here. This line is x equals y minus 1/16 y cubed. This line on this side is y equals x plus 2 squared. This one down, this point here is negative 2, comma 0. This is a straight line. And this is 0, comma negative 4. And this formula for x works good on both sides here. Okay, you can see it's not type 1. Right? You don't have that it's between two curves because, for instance, you're missing everything right here. It is type 2. But there's a point here. Why does it do this sometimes? Right there. So we've actually got to split this into two integrals. One down here, that's a type 2 integral. And then I'll do this one here. This is also a type 2. I just want to shade it differently so you can see the difference. So let's say you wanted to evaluate a function, and this whole region here is R over R dA. How would you do this? They give us a function integrate. 2x plus 5y. They do. Okay. Let's see if we can get this right. Well, this is one of the properties of integrals. I can rewrite this as the sum of two integrals. One over this region down here and one over the one up here. So the one down here, we'll call this R1. The one here, we'll call this R2. And now I have two integrals that are each type 2 regions. So I can set them up with y on the outside. If it's a type 2 region, I want y on the outside. For this lower one, y goes from negative 4 to 0. The function bounds for x are, let's try to draw these in. There's one right here, and there's one right here. What are those two functions? Well, the lower bound is a constant. It's just negative 2. The upper bound is this function of y here. Y minus 1/16 y cubed. This one's going to be annoying to integrate to, but whatever. This is dx on the inside and dy on the outside. Then I need to do the second region R2. Y now goes from 0 to 4. And x will go from this lower bound to this upper bound. Why do they do this way? This is ridiculous. I'm going to solve for x here. So x equals root y minus 2. If you take the square root of both sides. Hold on one second. Over there. I made a mistake because this is negative. So 1 second. Make sure I copied this correctly. No, no, no. Yes, y is okay. Square root of, yeah, that's correct, right? Yeah, sorry. Okay, so we'll use the lower bound root y minus 2, and the upper bound is still good. Y minus 1/16 y cubed, 2x plus 5y dx dy. So even though this is another example that the book chooses to give, it's going to come out to be ridiculously overcomplicated to actually work out. So let me just go a little bit into it. Again, I promise you I'll never make you guys do this kind of a thing, but if you integrate this, you get x squared plus 5xy between -2 and y minus 1/16 y cubed. That right there, put the colors around it again. The integral in x is right here. Let's do the second one, 0 to 4. Same guy, x squared plus 5xy, but now the lower bound is root y minus 2, and the upper bound is y minus 1/16 y cubed. So that inner integral there is now this guy here. And look, with enough willingness, arithmetic willingness, everybody can go and say, okay, x squared is y minus 1/16 y cubed squared. I can write this out. You can write this out, right? You're going to have a y to the 6th term, a y to the 4th term. You can also work out this guy. Here, I just plug that in for x. There's a couple more. We got to subtract off 2 squared. You got to plug in the -2 or -2 squared. And also subtract off 5 times, here x equals -2, y. Okay, all dy. It's just unnecessarily complicated. I still have to do the second one. Right, this is not an arithmetic class or an algebra class. We're not trying to give you guys problems where you've got to carry out long expansions of polynomials for no reason. But if you do this, well, okay, y squared minus 1/8 y to the 4th plus, is it 256 1/16 squared? I think it's 256 y to the 6th plus dot dot dot. All of this is easy to integrate. Y cubed over 3, y to the 5th over 5, y to the 7th over 7. But then you got to go plug in -4. You can obviously use a calculator. That's fine. It's just ridiculous. But anyways, let me just go to the other. So dot 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 is the remainder of the stuff that I'm not including. Then this guy over here, I'm gonna just put dot dot dot. Okay, well, no, no, no. So I want to make sure you guys aren't missing. So real quick, just this one part. Here, I plug in the upper bound for x. I have to square that. And again, I plug in the upper bound for x, excuse me. And then I have to subtract off what happens when I plug in the lower bound. And the second part as well. So y dy. Now again, this is a little harder because of the square root. Who cares? You can integrate fractional exponents, no problem. So the same deal here. Uh, you can plug in all these numbers and you'll get something. Um, and you can use a calculator, but it's a waste of our time to go through this, and I'm never, 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 never going to make you guys do something like that on an exam. I just want to give it one last reflection because, yeah, I don't know. I don't know why whoever wrote this book would do this, but whatever. Onward and outward. Okay, this is important. What if you're asked to change the order of integration? So let's say, for instance, you were shown an integral like this. And you were told, uh, change the order of integration and evaluate. Just to note here, you have to change the order of integration. If you integrate this with respect to y, you're going to end up with more stuff in x, and it won't be integrable. But if you do x first, there's a u substitution you can do here. Hopefully, if you guys look at this, you can see there's a u substitution. So you really want to do x first. However, will we achieve this? This is one of my favorite things to make students do. I think this is a great exercise, a geometric exercise. It's good for insight. It's good to demonstrate you understand what's going on. But from the student perspective, it can be frustrating because it's kind of hard. You got to think a little bit. What does this region look like? Right? They give us these bounds, and somehow they're describing a geometric region. But we weren't shown a picture of that region. So we must construct it just from what they show us. Well, they tell us x goes between 0 and the square root of 2. Here's 0. Here's the square root of 2. And for every single point between 0 and the square root of 2, y goes from 0, here's 0 down here, all the way up to 2 minus x squared. It looks something like that. Well, now here's the question. You can tell from looking, it's also a type 2 region. It's the area between two curves in the as functions of y. The lower one down there is x equals 0. And the upper one is, well, x squared equals 2 minus y, so square root of 2 minus y. If x goes from 0 to the square root of 2 minus y, and y goes from 0 to 2, it's the same region, which means this integral up here is equal to the integral from 0 to 2. X goes from 0 to the square root of 2 minus y. Whoops, sorry. Come on, give me my freaking pen. Minus y. Uh, x e to the x squared dx dy. Same number. By Fubini's theorem, this is the same integral. But we did it in a different order, reverse order. Look how different the bounds look. Right? They're not exactly the same. It can be tricky sometimes to work out this other order. But now that we can do a U substitution. This is 0 to 2. I need a factor of 2, so I take out a 1/2 to put in a 2, and I get e to the x squared from 0 to root 2 minus y dy. Everybody see that? If you plug in root 2 minus y, you'll get 1/2 e to the 2 minus y. If you plug in 0, you'll just get 1/2. And that's a very easy integral, right? This is equal to the integral. Well, you take the 1/2 out. You want to integrate e to the 2, e to the negative y. You get, well, that's the same as e to the 2 times e to the minus y. So negative, well, I'm saying, okay, I'm just wasting my time here. Minus y. You pull out the 1/2. Yeah. If you plug in 2, you'll get negative, that's 1 minus 2. If you plug in 0, you'll get negative e squared. Yeah, see, these are ridiculous answers. You plug in 0, negative e squared, y is just 0. So negative 2, so this is negative 3/2 plus e squared over 2. All right, that one's not so crazy, but I think I'm going to stop here. So I think there's a little bit more to say for this section. Let me just go back and check real quick. Yeah, there's a little bit more to say, but I'll pick it up next time so we're not digesting too much in a single day. So yeah, let me know if you guys have any questions. Thank you. Bye.